probably none of you would be here if you didn't have an idea what atmospheric CO2 is, carbon dioxide. You probably know more about it than your average Joe citizen. But I want to just add a few little things. You may or may not know about it. But one, we know there's a lot of greenhouse gases going in the atmosphere. There's carbon dioxide, methane, chlorofluorocarbons, nitrous oxide, blah, 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 blah. These are all important. We cannot ignore that. But by far, far and away, the largest contributor to global warming is CO2. It swamps everything. It's a huge, huge contributor. It's really fundamentally the cause of climate change. The second thing it does is you hear about ocean acidification, living on the coast, I'm sure you have. It's the cause of ocean acidification. You put more CO2 in the atmosphere, it dissolves into the water, and that makes the water more acidic, and the organisms in the water don't particularly like that. So as we keep putting up CO2 in the atmosphere, and you can see, and the little light doesn't work here, but as you can see, when measurements began in 1957 with Dave Keeling at Scripps Institution of Oceanography, and then NOAA picked up measurements about it in the 1970s and kept it going. This is a number that's not just increasing, but it's increasing faster every year. You can see here, it's a very low slope, and over here, it's a very steep slope. It's going up faster. When Dave started, carbon dioxide was going up 0.5 part per million per year. Today, this last year, it went up 2.5 parts per million, and that's what it's doing every year. So we've actually increased the rate that we're putting in the atmosphere, all while everybody is talking about, we're going to do something about this. So meanwhile, what goes into the atmosphere stays there a very long time. And I don't want to go into the details, but when you put CO2 into the atmosphere, what's left there after about a year or two is going to remain there for thousands of years. So once we put it in, we're stuck, unless we come up with a way to remove it, and we haven't yet, and it's not going to be easy if we try. So going to the next slide here, this is from yesterday. I should have grabbed it for this morning, but I forgot to. But you can look here, March 2015, CO2 at Mauna Loa is 401.52. Last year it was 399.58 on the same date. So we're measuring it every day, taking an average, putting those up there. And if we have a little time at the end, I can possibly reach out to that website and show you how that works, because anybody can get to it and download anything they want from it, including the movie I'm about to show. 400 ppm probably rings a bell to some of you. Back in 2012, we realized that all of our Arctic sites, out of a network of about 75 sites, we have a bunch of them that are up in the Arctic, reached 400 parts per million for the first time. Then, the next year, or next 2 years, I guess was 20. Whoops, somebody didn't check. Oh, this is okay. That was supposed to go down. There we go. So the next year, we saw the same thing happening in Mauna Loa, Hawaii. In other words, CO2 hits the high values of CO2 are showing up in the Arctic first, showing up in Mauna Loa next. This year, before it's up, the global average CO2 will have reached 400 parts per million. That includes stations like the South Pole or Cape Grim, Australia, but also everything. So it's going up, and that's what you would expect if you just keep pumping it into the northern hemisphere. But people hear about 400 parts per million. I get asked this by the press a lot. What does 400 parts per million mean? How do I get a grip on what that is and where we're going and where we've been and where the planet has been? So I'm going to try to show you some of that. We're going to go back here. Whoop, get back up there. I should be able to hit a click here and not have too much disruption. Nope, that was not it. Go back up. Try that one. Okay, I'm going to need a little, there we go. Anytime. Where's my Mac specialist? There she is. Let's guess it. You put that right? Got it. Okay. All it took was for you to show up. Voila. And then she tells me if I do a Command F, it gets big. That's exactly what I wanted to see. Okay, I'm going to show you the movie. We're going to start out here in 1979. What you're looking at is several things, obviously. One, you're looking at the observing system that we had in 1979. Those are the stations we were able to use that could measure long-term trends in carbon dioxide. There's not very many of them. There's 5 that are gray. Those are called background conditions. Those sites, because of their location and the wind direction, all that, capture air that has been across the ocean for a long time or isolated from human activity, so that you're getting something that represents a sort of an average for that latitude, longitude, etc. The red one is Mauna Loa, and the blue one is South Pole. These are representative of the 2 hemispheres. And then that light gray one is Niwot Ridge, Colorado. It's there for convenience because we're located in Boulder, Colorado, but it's high altitude, gets us some free tropospheric air, but it does pick up a little bit of air from Denver every now and then, and you see that in the record. So we're saying that that's locally influenced on occasion. What you see over here is a latitudinal gradient going from south to 90 degrees north. You see South Pole down here, Mauna Loa here, and then there's your background stations and your locally influenced station. So we're going to watch those as we go forward. We've got a clock here, and over here you're going to get a trace of Mauna Loa. It's going to show you the CO2 curve as it evolves, starting in 1979, and we'll start going back in time after that. Then it's from that point forward. Oh yeah, the South Pole continues to go up as well. So we're going to follow this a little bit. I'm going to make a few stops and try to make a couple of points that we have learned as a result of making these measurements that were very important. So I should be able to hit the click, right? To make it go? And push that. Yes. Okay, so now as you see this, if you watch the months here, it's January, July, October. Let's go back to July and see if we can stop it. Okay, a little further. Right there. Okay, we're getting into the summer. The northern hemisphere has plants. Most of the biosphere is in the northern hemisphere. Draw the equator through that line, you'll see most of the land is up there. And that's where your terrestrial plants are all growing. In the southern hemisphere, Australia is a desert, Antarctica is a desert, the lower part of South America is a desert, so you're not getting much. About 90 to 95%, I think the latest estimate was 92% of the terrestrial biology is in the northern hemisphere. So you're going to see that really kind of driving these swings. And in fact, you can see that here, because you get this oscillation that's 10 times bigger than the oscillation at South Pole. That also tells you that the biosphere is located mostly in the northern hemisphere. So let's let it run again. I think I have to hit the click. Yeah. Now you see that everything is going up because CO2 is going up in the atmosphere. Note how South Pole sort of captures the global trend without a whole lot of oscillation, and that's how it shows up over here. The background stations don't wiggle as much as some of these light stations, but we're getting at a point where I want to kind of put a halt to this right about here. Yes. What you're looking at is 1990. You can see we've got a fairly well-developed network now. We're able to monitor CO2 at all of these sites and get a very robust number. When we say the global average of CO2, we know that number to 1 part in 4,000. So there's really no question about that, and it's highly accurate. You can see a few of these little local sites there. We're trying to understand how the terrestrial environment influences the CO2. But another thing happened from these data. When we looked at the gradient of CO2 from here to here, and we looked at the gradient of another compound, it's called C13 CO2. In other words, it's an isotope of carbon that's locked into the carbon dioxide molecule, and it's supposed to show a certain trend. When you look at both of those, and you looked at the growth rates, you couldn't explain it based on what we knew about the Earth system. It turns out there was a huge, unidentified terrestrial sink for CO2. As we went further in this to study it and learn about it, we found out that, lo and behold, maybe it looks like about 1/3 of the CO2 emitted through automobile tailpipes, power plants, etc., in the United States can be accounted for by uptake, long-term uptake, in the North American continent. Now, politicians were very interested in this, right? Because if there came to any negotiations, they would say, well, gee, we're only emitting 2/3 of what you say we're emitting because we're taking it up over here with the land. But that was not our reason to continue with this. Our reason to continue was to try to understand the system a little bit better. So that was a big find, and it took that network to do it. You can't do it with 1 or 2 measurements, a little bit here and there, high calibrations, very high quality stuff. So as it goes forward, you can see the trace continuing. There's your southern hemisphere. It's off a little bit from the northern hemisphere, right? That's because summer is in January and winter is in December. So you're going to catch it. It should be exactly opposite, and that's exactly what it is. Notice what happened after 1990 here. Look how many local sites there are now. We've got a lot of partners out there collecting flasks for us, shipping them out so that we can analyze these and understand what's happening on the terrestrial environment. And we're getting a better and better handle on that. It turns out that half of the CO2 emitted into the atmosphere is either taken up by the ocean or taken up by plants on the land. We don't know the exact split. You hear different estimates, 50-50. I've heard 70-30 and 30-70. But the bottom line is we do know that half goes into the ocean and land and doesn't come back again, at least not in the near term. That's big. And notice the variability on some of these local sites. If you get close to a source, you're going to get a lot of CO2. We don't use those to compute global averages. They're just too locally influenced and too variable. We do use them to understand how the plants are breathing in and breathing out and taking it all. You also will see them go a lot lower because if they're near a forest, they're going to suck up more CO2 out of the atmosphere right nearby, and you get that. When you're taking your average, and we're just using these marine boundary layer sites, these gray ones, we have a good picture of what the global average is doing. Okay, now going forward, I'm going to let this run a bit. You'll see more sites go in and the Mauna Loa curve go forward. And then we're going to reach a point where these graphics is going to change because we got to go back a while. We want to look at it and see what was this all during human civilization. So what if CO2 is making it to 400 parts per million? And you can see that they'll reach, in the wintertime, it'll reach the higher value, and then it goes back down again. Every year, plants are making leaves and trunks and stuff in the spring and summer, and they are emitting the CO2 as they decay. Drop your leaves, they all decay, and you have CO2 going back into the atmosphere. Now look at all of the local sites that have gone in, because it's really a tough question that everybody's working on. We still don't understand it as well as we would like to, but it's a very robust number. It's not going to change one way or the other in the near term. So this is what we're going to do now. This is Dave Keeling's record, and Dave was the guy who started this whole thing. By 1957, he said, you know, I'm going to pause it at the end of his record here. Should be right about there. Okay. Dave had a hard time convincing people that he could provide the calibration scale and standards and make some measurements of something that was parts per million in the atmosphere at very, very precise levels, 1 part in 4,000. And he said, I need to do this in places like Mauna Loa and South Pole so I can have a picture of what the world is doing overall. So it was a bit of genius on his part. He didn't expect to see what he saw. He didn't expect to see the seasonal cycles. He didn't expect to see the trend go up like it was going. So he learned a lot from that, and so did the world, and we've gone forward. Now what's going to happen next, and I hope I can stop it in time, is we're going to zip back a little bit, maybe go back a couple hundred years, and we'll discuss where that is. Because I want you to understand the impact of human development on this cycle. We have a huge influence on this planet, and if you have a doubt about that, you can look at how many aircraft take off every day. You can look at those night lights pictures that are often put out by National Geographic, or you can look at the CO2 record and see what it's doing. So I'm going to drive it forward a little bit. Anybody have questions? All right. Go, baby, go. Okay, it's going to take a second here, and then it's going to jump on me. There we go. Perfect. Okay, now what you're looking at, notice there's two more sites here. There's one here at Law Dome, offshore of Australia, and there's the other one here at Sipel Dome. These are coastal Antarctic sites with rapid snow buildup, and so you can go back in a recent time, maybe not hundreds of thousands of years, but a few thousand years before you reach the bottom. Basically, you drill in and you take a piece of ice, you grind up the ice, and you measure the CO2 that's in the bubbles in the ice. Our colleagues at Australia started this mess, and they did a great job. These orange lines here are from the Law Dome site. You can see how they line up beautifully with the Mauna Loa record. So there's no bias, there's no issue with sampling problems and things like that. We have a nice, smooth record going from recent time, going back about the beginning of the Industrial Revolution, which is around 1750, 1800 or so. There's a couple of things to notice here. No, Sipel Dome, by the way, they've got fewer samples, but they show the same thing. So again, there's no bias brought in by the site we chose, etc. But this was really, really telling. Because we think of the Industrial Revolution, that was the 1800s, and first thought comes to mind is England with smokestacks spewing out smoke, and all over Europe this was happening, and the air was bad and everything. Well, from 1800, right here, to 1900, CO2 went up 10 parts per million, over 100 years. From 1900 to 2000, it went up 100 parts per million, 10 times faster. That is incredible when you think about that impact on the planet, because CO2 is a greenhouse gas. It's an important greenhouse gas. We wouldn't have life on this planet as we know it without CO2 in the atmosphere. It helps keep the planet from freezing. So, looking at this, and by the way, we haven't straightened out any lines. These have all the wiggles that you looked at before. The red and the blue and the green all have all the wiggles that you've seen before. So hang on to those because they're going to get a little tighter. Now we'll go back a little bit further, and we'll stop right about here. We see something a little strange, a little dip in the CO2 record. Anybody have an idea what that is? Little Ice Age, right? I heard somebody say it. It's the Little Ice Age. This is Shakespeare was busy writing, and several others. They like to stay inside. We had coffee houses, so you can stay inside where it's warm, fomenting revolution and creating things like democracy and all of that. All of that was happening during the Little Ice Age, and it was cold in Europe. It was miserable. But interestingly, note that CO2 went down too. So this says something about temperature and carbon dioxide. If you raise carbon dioxide, it's like putting a blanket on your bed. You're going to get warmer. But if you raise the temperature, it puts another blanket on your bed. It adds CO2. And this is something that confuses people at times. We're going to look a little more back into the record, and you can see how that happens. They have this sort of a game that they play. So if you don't stop one or the other, you're going to continue going, and you're going to keep going faster and faster. So there's a little ice age, and we'll go back a little bit further and try now. Let's do a little history lesson for everybody. We'll go back right about here. This period here is warmer. There's more CO2. There's more CO2 in this thing, and that's called the middle warm period. For 500 years, roughly between here and here, there was a civilization in Greenland. They had ships going in and out, farms, and all kinds of things along the coast of Greenland. It was big. So again, a small shift in CO2 associated with a significant shift in temperature. Okay, we're going to go back a little further. I notice the left graph is disappearing on you, so take a close look. From looking at these numbers, we can say the pre-industrial CO2 is about 270 parts per million. And yes, sir?
Could you just explain again why increased temperature leads to more CO2?
Yes, yes. It increases respiration on the planet. If you get warm, you breathe faster. Plants do the same thing. And soils respire more rapidly. So they're putting more CO2. So if you raise the mean temperature, you're going to kind of kick that up and put more into the atmosphere. It's
Plants don't take the CO2 out of the atmosphere?
they do that seasonally. Every season, every spring they're taking it out, and every winter they're putting it back because they're dropping their leaves and the leaves are decaying. Or the trees are falling over and the trunks are decaying, and all of those things go forward. So it's this cycle of carbon that's constantly going on among the biology on the planet. I mean, some of this gets washed into the ocean and it goes through marine cycles as well. That's more of a long-term thing. But yeah, the plants, if you just raise the mean temperature, you're going to have more respiration. You're going to get higher numbers over here. But notice this. We're about year 0 down here. Jesus was born, Roman Empire, Greeks were kind of starting in their decline. There was a lot going on. All of Western civilization, every bit of Western civilization was what? 280 parts per million, plus or minus about 5, 2, not much. So this is significant. This is a period in history where human civilization actually could survive and develop and evolve. Let's go a little further. And this is going to disappear on you there. And now we're going to go to another ice core from a different part of the planet. I'm going to go a little further here. Okay. This is the Vostok Ice Core, and we have that up here. The Vostok Ice Core runs from, it's in Antarctica. It's a Russian station. There was a big core down there, but that's a low deposition area, so you can go back very far in time with these samples. You just get a wide time interval between each sample. But you can see it matches up pretty well with this, as far as we can tell. But this is the bottom. This is the last ice age down here. CO2 at the last ice age was around 180 parts per million. Throughout most of human civilization, which goes back to where? The Egyptians 5,000 years ago, that'd be 3,000 BC. The Chinese, maybe a few thousand more, 5,000. Let's push it, say 10,000. It really doesn't matter. You're looking at 270, 280 parts per million carbon dioxide in the atmosphere during the entirety of human civilization, allowing us to have temperatures such that we could have agriculture, create cities, make inventions, invent the wheel, etc. Do all these things that we needed to propel society forward. I'll go a little further now. Take a look at this ice age. Hello, maybe. Here we go. Now, this is a 20 here, in case you can't see it. How long did it take CO2 to rise from 180 to 280 parts per million? 15 to 20,000 years. 100 parts per million, natural cycle, 15 to 20,000 years. We did it in the 20th century in how much time? 100 years. This is scary when you start to think about it. It's 150 to 200 times faster than we've seen since the last ice age and even before, which I'm going to show you. Now there is a curiosity. It's still in the ice age, but it's going to swing back again, and we can talk about that too, because it's a good example of temperature and CO2 influences. Okay, what you're looking at here, the ice age, we also call them glacials. There's another glacial. This is an interglacial, and this is an interglacial. Carbon dioxide is around 280 here. It's around 270, 280 here. Where was human civilization? Wasn't there. We don't have any evidence of it. It might have been, but even 100,000 years ago, we should probably be able to detect some resemblance of that. I mean, Rome was 2,000. We see lots of Roman ruins. Egypt goes back a little further. We should see something somewhere in the world. We see nothing. So here it was, ripe for agriculture, development, etc. This would have been Homo erectus, not Homo sapiens at that point, probably. But nevertheless, we just weren't quite there for that. I might miss that on the anthropology. I'm not an anthropologist. But the point is, that there were the conditions right there, just perfect, interglacial, 100,000 years ago, we didn't have civilization. This is a jewel. What we've got now is a jewel. Science, art, literature, everything we do. Let's go further. Now you see another interglacial and a glacial. Now the ice core record gets a little messy here because the integrity of the ice is not so good as you go further and further back in time. And there's shifting even beneath the continent in these big sheets. There's shifting and mixing up, and it's also hard to sample sometimes. So the basic idea is there. It's just not as clean as the recent years. The interesting thing about these cycles are called Milankovitch cycles, and they're named after a fellow who described them in terms of the wobble in Earth's orbit, which is caused by orbits of Jupiter and Mars. So we won't go into that too much. But the point is, that is a driver that drives temperature first and CO2 second. So the thing that stopped CO2 from going up here is that you kind of went to the next phase of the Milankovitch cycle, because you had that play off of each other all the way up and down again. By the way, down here, the geologists are all telling us that the temperature is about 4 or 5 degrees colder than today, Celsius. 4 to 5 degrees Celsius. We're anticipating that doubling CO2 will take it 2 degrees Celsius. What it means is that part of that is due to the increased insolation and part of it is due to the carbon dioxide. So it does help us filter those things out. Going further, another interglacial every 100,000 years. It's like clockwork, which is what it is. So this is the record as far back as we can go with measurements of carbon dioxide. There's other ways to go back millions of years by going into proxies like barium and that. But this is the CO2 record. Note, this 10,000 or 10 to 20,000 years here is a straight line. But on 100 years, and that's still got the wiggles in it, it's incredible. So what we've done is a huge experiment. And when we look back at this and think, well, 180, 280, 380, if you will, 100, 100, 100, 4 degrees colder here. Here it is, and we anticipate it's going to be a couple degrees Celsius warmer. Well, what is 2 degrees Celsius? 2 degrees Celsius is roughly 4 degrees Fahrenheit. 4 degrees Fahrenheit over the entire globe average. Most of that's going to be over the continents because the oceans will be more or less very small change over the oceans. So you got to multiply that by 3, in other words 12 degrees over the continents average. In some places in the continents will get warmer. What if it's more than 2 degrees Celsius? How hot's it going to get? How's our agriculture going to be? What's that going to do to immigration? What's that going to do to poverty? What's this going to do to opportunities to make money? And there's a lot of things happening here. But it's change. And we need to be prepared for change. We need to be willing to adapt to change. And we need to be able to try to deal with those aspects of change we don't like. Those are all tough decisions for society. I'm going to try to slip out of this if I can. Hit escape. So is there any questions while this is up? Because I can go back and forth. I can take this, I think, and make it go back by being a good boy. Whoop. Go right here. There we go. So if you want to go back and look at, hello.
Play again.
Oh yeah. Now you got to stop it, right? Oh, Macintosh. Okay. Okay. So we can stop anywhere we want and take a look at things. If somebody has a question, did I confuse everybody into silence? What do we have?
Besides the ice cores, is there any sort of like other chemical testing that you can do, say like volcanic rock or any other things that are being used to date further back to see if this point's ever been reached in the past?
The question was, can we go back further by looking at volcanic rocks and sediments and things like that in the ocean, et cetera? And yeah, the answer is yes, and people are doing that. And like I said, they're looking at proxies like barium and other isotopes to try to understand what it was. We do know about 3 million years ago, CO2 was very high on the planet, but it's a very different planet. And then if we go back to the Paleocene, Eocene boundary back around 60 some odd million years ago, it was pretty warm then too. But right before that, there were dinosaurs all over the place, and Denver was a marsh. So it is a different planet when those things happen. And human civilization has been at this 280 plus or minus 10. And that's where we are. Don't see a big change. Yes, sir?
Yeah, you talk about industrial revolution, and then this and the coincides with the deforestation that would have taken place in order to supply the industrial revolution. The replanting, of course, has been taking place the last 30 years. Has that had an effect?
I'm not sure on the question again.
Oh, the deforestation and the replanting of the forests.
Oh, forests. Oh, yes, yes. Well, one of the things that the United States did in the 1800s and Europe was get very busy deforesting the continents. We took down a lot of forest to put in farms, so you lose the longer-term storage. Forests do, not only does the carbon go into the tree trunks, but it goes into the soils, and that's where the long-term storage is. We don't quite understand how fast or how well that works. Certain aspects of agriculture do that, and other parts don't. So it kind of depends how we're working this. Like I say, we don't understand it. Going back in time, I don't think that's the real driver of the big changes we're seeing. Although when you go to an ice age, you have a lot fewer forests there to take up CO2 or to release it or even respire. So how that would play out either way is hard to say. But yeah. Yes, Mary?
So the slope of the curve, no, I'm not going to do
Okay.
it. You can repeat. So so that increase, the almost vertical increase, I've heard called the hockey stick. And
That's for temperature, right?
The hockey stick is temperature. Okay.
Right.
The CO2 is not the hockey stick.
Well, it looks like one.
Okay.
But no. The hockey stick is the temperature thing, and the data were a bit scattered. And Michael Mann put a line through it and said, you know, it really looks to me like there's a singularity here. And others validated that. And then it got to be a very stinky thing, and then it got validated even further. So, and that's related to what we're seeing here with CO2.
So I guess my question is, you know, that has been attacked by climate denialists. Does the CO2 record itself also cause some controversy? You get questions about the validity of it?
Yeah, we do. In terms of the validity, I think we've actually got that one put down pretty well and doesn't come up much anymore. In terms of the trends, I think people realize that this is happening. What they like to say, if you're a denialist, is that, well, we're not so certain that man's causing this. That's number one. The jury is out. We have to get more data, more information. That's good if you're a researcher, but it's the wrong thing to do. Another denialist thing is, well, we really don't know that much about CO2's influence on temperature. And you know, that's true. It's, when we say if you double CO2, what do we call it? Help me here, Ron. Climate sensitivity, thank you. The climate sensitivity for CO2 is about 3 degrees plus or minus 1.5 degrees, roughly. So there is some uncertainty there, but we do know that if you raise CO2, you're gonna cook things around you. So again, that's a bad one too, and we just have to admit wherever somebody says, I think there's uncertainty, say, yes, there is uncertainty, but there's only so much uncertainty. It doesn't mean we don't know anything. And that's the question, and that's the big fight we have. I think our biggest problem with climate change today is being able to communicate the issues to a society that is largely skeptical or unaware. And I say that because not everybody pays attention to everything. You guys are all here. I love it. I wish there was more of this. And a lot of places I can go and give talks, but it's only a small fraction of the world. So we need to have ways of reaching out and communicating, and this is where scientists need help, because you know, we can communicate with each other real well. We all speak the same language. But when we reach out to others, it's a little more difficult. And we're dealing with things like, most of you probably know Elizabeth Kubler-Ross wrote a book, The 5 Stages of Grief. one of my good colleagues, Steve Running, posted a website that had the 5 stages of climate grief. And I thought it was good because they're exactly the same. First stage, denial. First thing is, oh, not happening. I don't believe it at all. This is BS, you guys. You don't know what you're talking about. Your uncertainties are too big. The next stage, so they ignore what's going on. The next stage is anger. What do you mean it's going? I mean, this is going to do this? No, it doesn't matter. I'm going to drive my SUV anyway. I got to do all this other stuff, you know? And that goes on. The third stage is bargaining. This is what I call the Al Gore effect. Al Gore was great when he said he still can drive his SUV because he's buying offsets. Never mind that we have a hard time measuring what those offsets are doing or if it's actually making a difference. He was buying the offsets. And you can go on the web and buy your offsets. That's bargaining. Saying, well, I still want to have my lifestyle. I still want to do the things I'm doing. I don't want to change our energy source. Don't want to do those things. I'm going to try that. The fourth stage is depression. Totally like, oh man, we're screwed. and then you just get bummed and you can't do anything. You can't get up out of bed. It's awful. The last stage is acceptance. And this is where you accept what's happening and you move forward. Scientists love to think that we're at the stage of acceptance. I disagree. And this is depressing. You can plug your ears if you don't want to hear it. I think scientists are still bargaining. We think we can do something about this. And I worry. Because when we hit depression, it's not going to be pretty. So I hope that we can find ways, because I'm not going to give up. I hope we can find ways to communicate better to society what this is and what it means. How do you go to the guy in Georgia driving his truck and he's got a small family with a few kids and trying to make a living and he loses his job because they just shut down something in the timber industry? How do you get him to think about climate change when he's got to feed his family? How do you do it? I don't know. So that's the thing that we need to be thinking about. We need to reach out to, what was it, Herb Cain? Was Herb Cain or, yeah, it was Herb Cain back in the 70s and 80s. Used to refer to Joe Sixpack. Remember Joe Sixpack? Yeah. How do we reach out to Joe Sixpack and get him to understand this in a sense that he really wants to do something about it? There's so much we can do. One, we know there are renewable energy options. We know there are efficiency options. We know there's a lot. In fact, we can actually get off of fossil fuels entirely and have more energy than we have now. That's possible because the sun shines everywhere and it's a huge amount of energy. We just have to find a way to use it effectively and transport it. These are issues, easy to do. Got a man to the moon in 8 years. Not bad, when we couldn't even get a rocket off the ground. If you remember the Vanguard, flopped about 3 times before they finally got with the Explorer up, and it barely made it. So those were challenges. The one nobody mentions that I think is even bigger than the moonshot is World War II. The United States was attacked on December 1941. That means we really didn't enter the war until 42. Halfway through 45, it's over. We didn't have a plane. Half our Navy had just been sunk. Our Army was in disarray. We just didn't have anything because we were just gone through the Depression. We'd gone through this whole thing of isolation. Didn't want to do anything. 2.5 years, 3 years, bingo. We pretty much flattened Europe, pretty much flattened Tokyo and Japan, and basically supplying all of our allies with all of the equipment that they needed to help fight the war with us. It was an incredible act, and it was done in a very short period of time, and there was a national will. So when you talk to me about renewable energy, and I have my friends in the National Renewable Energy Lab saying that, oh yeah, from a small little teeny patch in Arizona, we can provide 7 times the electrical power that we're using today in the United States. All we're lacking here is a will. I'm not speaking as a representative of NOAA when I say these things, but it is trying to provide ways to get a solution, and it's going to require communication to make that happen. That was a long answer to a short question, I think.
So I want to thank Jim.
We're done.
you can stay here longer to talk.
I like to talk too much.
I just wanted to make sure, because some people actually are on their lunch hour, that if people needed to leave, they could leave. That was a fantastic talk, and we can have more questions, and people have them.
A very interesting description of how the CO2 was measured in the last half century. What missing CO2 measurements are there? In other words, if you could measure it the way you wanted, what would you like to have and why would you like to have it?
Excellent question. What we're working on now is we get the global trend very well. We're not worried about that. We get the global distribution quite well. We can tell you each latitudinal band, what the average is there. That's all very straightforward. But what we can't do is provide the kind of information that people are going to want 10 years from now at policy relevant scales, on time scales and spatial scales that say, gee, Governor Brown, your efforts at reducing greenhouse gas emissions look to be working for the most part, but we see a problem in your power sector, but your automobile sector is doing just great. Basing this on atmospheric observations, which are completely independent of inventories and all of those other things, we can say, is the atmosphere consistent with what you're saying you're doing? And if not, here's some information for you, see if you can work on the problem. We're just scientists, we don't want to regulate somebody or fine anybody or any of that. We simply want to provide information. And this is a global effort. We're working with the World Meteorological Organization on this to try to fill these gaps in both space and time so that policymakers, resource managers, Joe Sixpack can all make good decisions based on good data. So we need more observations and we need better transport models than we have to keep it all globally coherent.
Yeah.
Oh, he's got the mic there. So.
Over there next.
Okay.
I was going to ask, coming from a position within the government, how do you feel about the changes that are going on in the government now?
Am I allowed to answer that question? I worry about any change in government. It doesn't matter what it is. You can overreach, you can undershoot, you can do all of those things. But I think I'm a little worried this time. If they want to cut funding for research, not just in climate, but a whole bunch of things, to me, that's heresy. But I'm a scientist. I do think civilization has gone forward during this time we were looking at, since the Industrial Revolution, in good part because of advancements in science. And I think the Romans would agree with that, as would the Greeks. That those are the things that propel their society forward. So if we refuse to invest in the future, we're going to be left behind. It's that simple. So I worry about that, and that's my biggest worry with Congress.
So I wanted to ask if, when you said when scientists get depressed, would scientists get depressed because it's so damn slow to convince people in power to relinquish what's going on? Or are you saying that there is no irreversibility of what's happening now, or both, in terms of what's happening with climate change?
The one-word answer would be both, but I think there is some flexibility on this. One thing that scares us a lot, I mean, humans are not facing this. I mean, CO2 keeps going up more and more every year. We say we're doing these things, which is what that last slide I'm going to show you here before we're done. We say we're doing things, and yet it's not working. That's what gets us depressed. And so we worry about that. But there is something, it just came out, the National Academy of Sciences came out with 2 reports called Climate Intervention. This scares us as scientists a lot, because the idea is to intervene with what the climate is doing to try to make it so that we can still have good conditions for humans on this planet. Wow, that's a lot. And they broke it into 2 categories. One is CO2 removal, and the other one is albedo modification. In other words, changing the reflectivity of the surface of the Earth. The albedo modification thing was proposed years ago. You say launch rockets up into the stratosphere, put a lot of particles there, and they'll reflect the sunlight, and you won't be warming as much of the planet. This happened when Mount Pinatubo went off. It happened when El Chichon went off. Whenever you get these big volcanoes, they put something up there. It stays there for 3 years, and then comes back out again. But to deliver what a Pinatubo does, takes many shuttles worth of particulates if you're going to be launching. And to sustain it, I calculated a while back, I wish I could remember the number exactly, but I think it was like 50 shuttles a year, continuously, forever, to just get the Pinatubo effect, which is about a half a degree, maybe, or a degree. So that's Fahrenheit. So it really, it doesn't do it. But the climate engineering is something, when things really get bad, and they haven't done the research to understand the system, haven't moved into these other things, that's going to be invoked by politicians, by industries, by shysters, by all kinds of approaches here. It's going to be pretty bad. We want to be able, and we're trying to, say, well, okay, let's gather our information together and try to inform these questions and decisions that go forward with the climate engineering. That's scary too. So those kinds of things are scary. And most of us can't give up. So, yes.
Yeah, I have a comment. First, I want to thank you for this fantastic presentation and these keywords like scary and realistic.
Apologize for that.
No, but it's true. And I want to make a comment on the stages that you were talking about. There's the depression stage, which is super real, and then there's the maybe I need to accept this stage and move forward. So I just want to make a comment that in this last 100 years of our civilization, we have this new thing called the internet, which could be the answer to the communication piece that you're putting. And I just want to make a comment that just less than a month old, there's a new top-level domain that's green, and it's putting that into the hands of the people to communicate, to share the science,
Excellent.
to share business, to share what the consumers want. We can use this top-level domain to spread awareness. So it's the internet's one way to do the communication question that you asked.
That's excellent. Because that is a big issue. Yes, sir.
Yeah, this analogy that you used earlier about the blanket on the bed, like an electric blanket on the bed, and I can just envision turning up the blanket to high, which is kind of the direction we're headed right now. Can you expound a little bit more on that? Because I talk to people all the time that think that we can just turn the faucet off on CO2, and if we just ramp down what we're pumping out right now, we're going to be fine. But it's not that easy, is it?
No, it's not. And thank you for asking that. The electric blanket analogy is one I use more than I do the adding blankets, because it's almost perfect except for one thing. Imagine electric blankets you can't turn down. So you're lying in bed, you've been in the same bed for 20 years, and you're always just a nice, comfortable temperature. You decide one night to raise it up to 4. You think, it's not so bad, I'll raise it up to 5. Yeah, it's still fine. The reason is there's a lag. There's a lag between the change in temperature and the increase in CO2. We've put CO2 100 ppm up there in 1 century. Remember that last one that had 10,000 years to evolve it. So it's going to take a little while. It won't take 10,000 years, but we're going to see things cooking up. If we stop emitting CO2 today, temperature's still going to go up because it's got to catch up with what we've already done. So we can count on that. You want to get into acceptance, that's one of the things we have to accept, that that's going to happen. Unless we come up with this climate intervention thing, and we don't have ways of doing that yet. Not on a level. We're putting in 10 billion tons a year of CO2 into the atmosphere. Imagine removing that. That's a lot. And where are you going to put it? And what's it going to be? So those are issues. Yes, sir.
All right. I was trying to figure out how to phrase this. Because of the increased warming due to CO2, the permafrost is melting and creating methane releases. And is methane affect the amount of carbon dioxide increase, or is it just another gas that we measure separately?
Methane is another gas that we measure separately, but we measure it right with CO2. They're both carbon. Methane is CH4. Carbon dioxide is CO2. They're very close to each other. Methane has a global warming potential of 25 times that of CO2. But methane is measured in the parts per billion, not the parts per million. So you increase methane, it still has a temperature effect because of that, but it's not as bad as you might think because it's not equal in concentration to the CO2. But the methane, when it does get destroyed, it turns into CO2, so it adds a small amount of CO2. And it has a shorter lifetime, about 10 years. But if a lot of methane comes out fast, it's going to warm things up fast and drive more CO2 out. And that sets up another nasty little cycle. And then we could end up having it out of our control entirely. We worry about the Arctic. We know methane has started going up again after not going up for a while. But we also know that it's not the Arctic releasing it right now. It's mostly in the tropics. And we know that from this network. We can tell that. Yes, ma'am. Oh, I'm sorry. Right here. She's in the back there next. Okay. In the orange. Yes.
First of all, to thank you for this opportunity to come and learn about this subject that I'm totally not aware of. And from a layman's point of view, my question to you is that we are very privileged to come here for free. And then also we have delicious lunch provided. In countries that are poor and people have problems surviving, how are we going to become a global concern and awareness?
Two things on that. One, you're absolutely right. I mean, that is an issue. Most of the world is impoverished by far, and we are very well off. We use most of the resources. We emit most of the CO2 by far. And so, United States, Europe, China, these countries can talk to each other. These countries can manage and do things. If we can control most of that, we're in good shape. If we cut CO2 emissions by 80%, okay, so only 20%, that will allow us to hold CO2 where it is without going up, at least for a short period of time before it starts taking off again. If we cut it by 90%, it'll be a very, very long time before it goes down. So the first step is let's get the industrialized countries, parts of the world, to get on board. The rest of the world will follow. And I think the third world deals with a lot with, we don't call it the third world anymore, the developing world, deals a lot more with air quality than they do climate, because that's an immediate concern. And that's something we relate to very well. We evolved on this planet under conditions that said you will survive, not if you think long term, but if you think about feeding your family and keeping the wolves at bay and building the fire. Right. Yes, ma'am.
Yeah, my concern is you get more consumers, you get more demand.
Yeah.
So is population control a viable tool in reducing CO2 emissions?
The answer on that is no. Because it's going to control itself. And I don't mean that in a devastating way. There's a fellow named Hans Rosling, gave a wonderful talk when I was at a meeting in Copenhagen, and it turns out he has a website called Gapminder, gapminder.org. I don't know if any of you have been on there, but he has a wonderful one about the birth rate. You can choose statistics any way you want to and plot them all kinds of different ways. But he asked everybody at the beginning, he says, okay, the world's population when President Kennedy was in was 3 billion. Today it's 7 billion. We've more than doubled it since Kennedy was president and launching or thinking about launching something to the moon. That's a lot. That's huge. And it's continuing to go up. So he says, where do you think this is going to go? Do you think it's going to go up like that? Do you think it's going to go down like that? Going to follow some path upwards? Is it going to level off? What is it? And he showed, based on statistics from all the individual countries, he says, it doesn't matter what country you're in, whether you're rich, whether you're poor, whether you're Christian, Muslim, or Buddhist, or whatever, all of those ways of cutting through society, he said, it doesn't matter. Birth rate is going down fast everywhere. He says the decision is being made in the bedroom. People are saying, I don't want to have a big family. It's not going to work for me because I'm impoverished. It's not going to work for me because I'm rich. It's not going to work for me because I have opportunities in the world. All of these reasons add up to say, and he said, I can tell you with almost absolute certainty that the world's population will level off at 9 to 10 billion. Now, that's a lot, but it's not over twice as much as we had in 1960. So can we deal with this? Probably. Now, does that mean we don't have too many people on the planet? No, we do have too many people on the planet for what we're doing. The damage we're doing to the planet is way beyond just climate change. I mean, it touches on everything. Species loss, resource management, and a number of other things. So there's a lot of things come into play with this population thing. Unless we get a grip on them, just like we need to get a grip on what we're doing to cause climate change, which we can do, we're heading down a bad path. But I think looking at those things that we're doing, envisioning them with the large population that we have, and say, how do we deal with this in a way that keeps our diversity on the planet, keeps the temperature in a reasonable place, allows us to continue our agriculture without huge modifications, would be a good thing.
Jim, I think we need to wrap up, but I want to see your last slide.
Oh, this last slide, I wish you could read it. I was getting on the plane in Frankfurt, Germany, and it was last Thanksgiving, and I picked up a copy of Die Zeit, one of my favorite newspapers over there, and I started reading through it, and I got through the front page, a few of the key articles, like to know what the Europeans are thinking, slipped over to the editorials, got bored, went over to Die Wissenschaft, which is science. Flipped over to opened it up, and there was a full-page spread titled "The Tricks of the Climate Politicians." Die Tricks der Klimapolitiker. Anyway, I translated it so I could show it, but it doesn't. The granularity is not as good as I would like. So let me escape out of here, and just how do I close that out? Go back over here. Can't I just
click on your window here. Just click on the.
I want the PowerPoint.
There you go.
Is that it?
Yeah.
Hello. What to do? Okay, so now I can go down a slide. There it is. Tricks of the climate politicians. Now, this is why scientists, where's the lady? Oh, she's not here, that asked about being depressed. This will make us depressed. Here is the black line is the emissions that we've seen up to today. This is in the newspaper in Germany, a full-page spread. Think about this. And the brown line is business as usual going forward. That's CO2 in the atmosphere. The green line is where we need to go to keep the warming at 2 degrees Celsius. And remember, 2 degrees times 2 times 3, etc. That's our target. The target is way too high, but that's okay. Let's try to get there. You got to start somewhere. The problem is the solutions here, Germany says, well, we're going to base our reductions 40% from 1990. European Union follows and says 20% from 1990. They just recently upped that to 40% from 1990. That was good. They're both consistent on the year, both consistent on the amount. US says, well, we're going to use 2005. You know why? Because that's before the economy collapsed. And they can use that year because it was a natural drop in CO2 emissions during our collapse of the economy. And they're saying, oh, we've already reduced ours. China and India both chose 2005 and have even weaker commitments than the United States. They went in and added all this up and said, what's this going to take us to? It's going to take us to a 3.6 degree world, on average, Celsius. So it's not pretty. I'll let you do the math on that. The tricks that we do, there was the different baselines, as they mentioned. Another one is the offsets. Britain says, well, we're going to be emitting too much, but we're going to buy offsets from Brazil. Then Britain will count the offsets in their emission counting, and Brazil will count the offsets in their emissions counting because they're growing the forest, and you get double counting, and that's going on. The other thing is using an outdated scenario like the United States, which picked right before the Depression or the recession to capture a loss that would have happened anyway, so it didn't represent any effort on our part. That's what we're doing. And that's where we're going at best, because we're not likely to make that one too. So yeah, this is what makes a scientist depressed. but we're not giving up.
Okay, on that note, but I do want to thank you so much.
Oh, thank you. This has been great. You've been a great audience. I appreciate it, and thank you.